Welcome to Robotics and Automation News webinars, where you can be part of a global event without leaving your home or office. Attend our live webinars and communicate directly with influential professionals in your industry.
My name is Abdul Muntakim. I'm editor of Robotics and Automation News.com. Today I'll be speaking to Mark Ring, co-founder and CEO of CogitAI, or CogitAI, a startup company which has developed new kinds of artificial intelligence. Most people have probably heard of machine learning, a type of AI, but CogitAI has developed something it calls reinforcement learning. And now it wants to go one step further and develop something it calls continual learning. The basic idea is to create an AI system which is capable of learning by itself and making decisions which it acts on all by itself. Mark will make a presentation about CogitAI with support from Dennis Crespo, the company's VP of Marketing and Business Development, and I'll be asking questions at the end.
CogitAI is an AI company, and these days that doesn't seem very unusual, a lot less unusual than when we started in 2015. These days it seems like every company has to be an AI company. In fact, I have a friend who recently joined a company, a startup. It has nothing to do with AI at all. But they found out when they went for funding that none of the investors wanted to invest in them because they weren't an AI company, and all the investors wanted was AI companies. So they had to go back to the drawing board and figure out how they were going to sell themselves as an AI company, because that's the only way they could get an investment. So I know it's very common these days. Everyone says they're AI companies, but we really are a very deep core AI company, and that can be made clear in three different ways. First is our team. The second is our product, the kind of AI that we're focusing on. And the third is our long-term ambition. So let me say a little bit about our team first and how we got started. So our team is one of the core AI teams, one of the collections of the people who really began the field of reinforcement learning. Because of the strength of our team, when we first decided to go out for looking for seed funding, Sony heard about us. Sony had direct connections to us and to our team, and they immediately wanted to invest. So within a few days of their hearing that we were going to create a company, they told us that they wanted to be our seed round investor. They knew about our work, they knew our people, they knew what our vision was, and that was something that they could get behind immediately. So we were founded in 2015. We soon thereafter got funding from Sony, and Sony today still remains a major supporter and a great partner in the work that we're doing. So if you look back to the very beginning of the field of reinforcement learning, you'll find that there were just a few people. This was in the late 80s, early 90s. There were really just a few people in the field at that time. We didn't really even have a name. Eventually it came together as reinforcement learning. But most of those people are very well known now, and most of them are associated with CogitAI in some way. I was one of the pioneers in the field. I also created a field called continual learning, which is taking off today. At the last NeurIPS conference, we had a room with 800 seats. Sometimes it was standing room only. So people are really starting to get interested in continual learning as well. My co-founder and the president and COO of CogitAI, Peter Stone, is also one of the pioneers in reinforcement learning, especially reinforcement learning and robotics, one of the first to be able to deploy reinforcement learning and robotics successfully. He and his team are one of the winners of the robotic soccer competition, RoboCup, nearly every year in at least one division. He's made fundamental groundbreaking contributions to this field. Our VP of Engineering is Pete Werman. He has a PhD in AI, but he was also the Chief Technical Officer and co-founder of Kiva Systems, which was the warehousing robotics company that was bought by Amazon for nearly $800 million a few years ago. He was the head of Amazon Robotics before coming to CogitAI. Our VP of Marketing and Business Development, Dennis Crespo, is not one of the founders of the field of reinforcement learning, but he has been extremely successful in bringing AI companies to market and is a great member of our team that we've just started recently. But if you look at what happened at the beginning of our company, we were able to go to really the founders of the field of reinforcement learning, like Rich Sutton and Andy Bartow, Satinder Singh. These guys, if you look into the history of reinforcement learning, you'll find out that these are the people who really created the field, who created the framework that the entire field has evolved from since then. And it was easy to get them all on board. They were all colleagues of ours, friends of ours, and that we've been working with and collaborating with for several decades. So after we brought the Brain Trust on board, our technical advisory board, and got funding from Sony, we were able to start hiring. We now have 20 people, 15 of them are PhDs. Almost all of those PhDs are in reinforcement learning. So when I talk about our team being very different from most AI company teams, it's really true. We have among the best talent in the world in any AI company, and especially in reinforcement learning and continual learning. So now let me say something about the product. So in the second way that we're differentiating ourselves is because of the kind of AI that we're developing. So we're not just creating an application for current AI. We're actually moving the ball forward. We're developing new AI technologies, the next generation of AI, starting with reinforcement learning. Now, the difference between standard AI and reinforcement learning is vast, and I'll explain that to you right now. Almost all, probably 99% or more of AI applications today use what's called supervised learning. Supervised learning requires a human to label data, and the algorithm finds patterns in the data that match those labels that were supplied by humans. Now, this is extremely powerful because it's really good at finding those patterns and being able to predict what would a human label this as. But that's all it does. So we tend to think that AI can do a lot more than it really can do. This is the major power of AI today, is being able to guess what would the label be that a human would put on this particular data sample. Now, a lot is missing from that picture. In particular, the ability to make decisions and to learn from those decisions. That ability is nowhere to be found in the supervised learning story. So I like to think about it as that supervised learning is like the sensory cortex of the brain. It can do the data analysis, but that's it. It doesn't do what the executive cortex does. It can't make decisions. It doesn't do what the motor cortex does. It can't take actions in the world. For the rest of that picture, you have to go to what we think of as the next generation in AI, which is reinforcement learning. Reinforcement learning has been used very successfully in solving certain problems that simply can't be done with supervised learning. For example, playing the game of Go to performance better than human performance required reinforcement learning. In the game of Go, the learning agent makes its own decisions. At every move, it decides what move to play, and it plays till the end of the game. And at the end of the game, it finally finds out whether it won or lost. And based on that signal alone, it has to figure out, well, which were the good moves and which were the not so good moves throughout the game. If it plays the game millions of times, or maybe hundreds of millions of times, then it eventually can figure out what the best moves are in every situation. So in the reinforcement learning case, learning is really a loop. It's a feedback loop. In the supervised learning case, the data comes in and an answer comes out, and that's the end. In the reinforcement learning case, data comes in. We call these observations, and they come into what we call a learning agent. And the learning agent makes a decision and takes an action. That action is then played out in the client's process. And what happens as a result is the process changes and a new observation is available. That new observation then allows the learning agent to make another choice, another decision, to take a different action. And this process continues over and over and over. And from time to time, the client process can also send a signal to the learning agent, a reward signal that tells the agent how well it's doing on this task. Depending on that value, the agent can adjust the actions it takes in response to every one of the observations in order to improve its performance, to drive that value higher and higher and higher and higher. And that's what the technology of reinforcement learning can do. So it's very powerful, and it's doing something fundamentally different from supervised learning. Generally, in supervised learning case, in AI today, the data is analyzed, and then that's given to a decision maker. The decision maker could be a human who looks at the data, the analyzed data, and then makes a decision about what should be done with that data. Or it could be an automatic process, a script of some kind that takes that data and then makes a decision automatically. But in neither case is the AI itself making the decisions and then learning from those decisions to improve the decisions themselves. And that's what we can do in reinforcement learning. Learn to make better and better and better decisions. So it opens up an entirely new world that AI can be involved in commercial applications. It allows the AI itself to make decisions and improve those decisions. And usually, or nearly always, it's doing this in a way that humans just can't do. Maybe humans are overwhelmed. There are too many decisions that need to be made for any human or any group of humans to be able to do. Or maybe the decisions just have to be made much too quickly. For example, inside a car, every time a spark plug fires, a decision has to be made. When is the right time to fire that spark plug? A little bit later, a little bit earlier has a big impact on the fuel efficiency, the emissions, the performance of the car. But obviously, a human can't be there to make a decision about when to fire that spark plug every time. So instead, there's a controller in the car, and that controller was created by a car engineer who came up with an ad hoc method to try to get the best performance. So what we can do is learn in every car individually what is the best action to take at every step to get the best performance, depending on what it is we're trying to optimize. And this is the power of reinforcement learning. But reinforcement learning itself has limitations. And being the founders of this field, being the pioneers in this field, we've been working in it for 30 years, and we understand what those limitations are. In particular, reinforcement is fantastic for optimizing a relatively simple system that can be repeated an indefinite number of times. So like the game of Go, it can be repeated millions or hundreds of millions of times, go back to the beginning every time, try again, and learn a little bit more every single time. But in the real world, we often are confronted with systems that are more complex, that are too complex, or that can't be begun all over again. In those cases, we need to go beyond reinforcement learning. So we think of a third generation is the continual learning generation, where we're going to go beyond reinforcement learning. So supervised learning we see as the first generation. It's been extremely, extremely successful in commercial applications. We think reinforcement learning is going to make supervised learning seem small in comparison. 10 or 20 years from now, we're going to look back at supervised learning, and we're going to think of that as just the first step of AI in commercial applications. We're going to see most of what's interesting about AI and most of the work that'll be done in AI will make that look like the thinnest sliver, will make supervised learning look like the thinnest sliver of AI and its impact on commercial applications. Now, beyond reinforcement learning, we want AI systems to be able to remember what they learned in every situation that they're exposed to, remember the abilities that they developed, and be able to reuse those and reapply them in new situations. And that's really, really hard, even impossible for reinforcement learning systems to be able to do. Because of the fundamental theory and foundation of reinforcement learning, it's extremely difficult, if not impossible, to take what was learned in solving one task and being able to apply that in new, novel ways and new situations, which is something that's going to be required, especially in a field like robotics. The long-term future of robotics is going to require us to be able to teach robots to do simple tasks, and then you need to be able to depend on them once they've learned that they're not going to forget it, and that we can use that and build on top of it to teach it more and more sophisticated kinds of skills and knowledge. And that's what continual learning is all about. So to put it very, very simply, there's this deceptively simple diagram I like to show here. This really captures quite a bit, actually. What we need to be able to do in the continual learning case is to build skills, lots of skills, have a library or repository of different skills, and then be able to use those for generating knowledge. So with more skill, there's more that you can find out about the world. And then use that knowledge to be able to generate more sophisticated skills, and use those more sophisticated skills to understand the world better, and so on in this continuing ladder of building up skills and knowledge. And this is really the bedrock of the third generation of AI, continual learning. And this is a part of our vision. So this is the third point, getting back to the third point that makes us different from other AI companies, is this vision, is that we're building towards being able to develop systems that can themselves build up their own skills and knowledge in this ladder-like fashion. So I'm going to talk a little about the use cases. How do you use this technology today? But first I want to talk a little bit about our platform, which is our primary product. So imagine that you're one of our clients and you have a use case like is shown here on the left. Maybe an automotive use case, or video games, or user engagement, or an embedded IoT system. We're going to show on the next slide a bunch of other possible use cases. The way that you interact with our platform, Continua, is first by creating an account. So the user is going to go to Continua, it's going to create an account, and that will allow the user to specify in a formal language what the the client's use case is going to look like. What is the interaction going to look like between the client and Continua? Once that's specified, then the client sends information, sends data to the platform. And based on that data, then Continua provides a decision. So it sends a decision back to the client. Then the client executes that decision in the client's own use case and sends a new data sample to Continua. And this process continues again and again and again. And from time to time, the client can send a reward signal back to the platform, back to Continua, an evaluation signal, a signal that tells Continua how well it's doing with the action choices it's made so far, and helps Continua figure out what it can do to improve that signal. So it's a measure, it's a performance measure that Continua is trying to optimize and can continually improve. And that's all there is to it. So it's just this loop of back and forth plus the occasional reward signals, and that's the whole interaction. And because it's so simple, it can be applied in many, many different possible use cases across many different possible sectors. So let's look at what some of those sectors are. And this is where I think it'll be helpful to bring in our VP of marketing and business development. So I'm gonna have him join us, but I'm also going to give a little bit of a preview. So we've looked at many of these use cases shown here, plus many others. We're working with certain manufacturers already. We're working with one of the world's largest auto manufacturers right now, and trying to do reinforcement learning and continual learning inside the automobile. We're currently working on a project with them to do that will move towards licensing of the Continua platform down the line. Right now I've got Dennis Crespo on the line, our VP of Marketing and Business Development. So I'm going to let him discuss the use cases here, because I think he does a better job of describing those than I do. Dennis?
Okay. So a few years ago, we were contacted by a top 5 automobile maker for an application that wasn't autonomous driving, which is interesting because you can use our technology for that. It was really controls of the internal systems around the engine management of the car. So this is a fuel system, spark plug firing, exhaust systems. So our learning agent can learn how a car works from the inside out, including the driver, and including how the driver reacts in different situations. So the goal here was to increase mileage and performance depending on the situation. So the learning agent would monitor the car during its normal operation, taking a huge amount of data every day as you drive the car. And then it would create scenarios in which the engine was managed much more efficiently to get higher mileage when you weren't asking for performance, and different scenarios when you were asking for performance where it was giving you more of what the engine can handle. So so that started our progression in the automobile market. We think this can apply to other manufacturers as well, and it can apply to electric motors as well as regular gas power plants or diesel power plants. Same idea goes here for electric motors. We're looking at all the systems in the car, and we're tuning them for efficiency depending on the driver's habits. Now, this application also works in a large network sense. The car manufacturers that we're working with desire to maintenance the vehicles and manage the maintenance life of the vehicle so nothing gets destroyed if the vehicle isn't maintained properly through this engine management technique as well. And then when it's brought into a service center, you can upload that profile of all the learning that happened on that car during that period. And then that is shared with the rest of the network cars in that same network from that manufacturer. So learning in a cold weather climate in country A will apply to a cold climate in country B. And the same thing goes for warmer temperatures or different driving habits. So there's a global learning technique there as well. And then the rest of that data, after collection over time, goes into the design of a new vehicle in terms of how to make this more efficient. Of course, Mark probably mentioned this through the presentation, we were involved in robotics projects. We will continue to be involved in robotics projects as reinforcement learning and continual learning down the road really apply to this type of use case I would say, apply very naturally this type of use case. But that learning from the robotics side can be applied to manufacturing as well. Manufacturing arms, one of the biggest challenges is using these robots in manufacturing. It's programming the robot can take months or even longer, large teams of engineers to try to route plan for how to make that robot react better on a manufacturing line to a new product you might be building. So our software, of course, will learn how to take the correct route to build that product through autonomous learning, but also a human assist process as well, where you're giving cues to the robot on the right path to take, and then it'll do some more learning on its own to perfect that path. So it speeds up the manufacturing process of deploying these robots into the manufacturing line, but also reduces the time and effort, engineering effort in doing that deployment and service costs for maintaining the robots. So that's kind of a big win all the way around for manufacturing. In the supply chain as well, where you're looking at lots of different options for shipping or managing your inventory, and you want to make decisions there to make sure that you're not overstocking inventory to kind of adjust in time, but also you're able to ship to your client in the most efficient way, the most cost-effective way in that given moment in time. And so there's lots of data mining there, and lots of decisions need to be made. And currently right now, those decisions are made by a human, and you really can't scale that to millions of customers. So having an RL engine or an AI making those decisions and smart decisions is really necessary. In video games, there's an infinite amount of opportunity here. So the game environments themselves, how they react to players, how players react to those environments, you can start learning that and then changing those environments real time within the game to keep challenging players and keep them interested. Today, it's the content is very diverse and a very large world. However, good players seem to solve the harder puzzles in a very short period of time, like literally overnight from the release, which means that the content manufacturer, the video game publisher, loses subscription services very quickly after the video game was released. Their goal is to keep people involved for months. When the harder puzzles are solved in a matter of hours, it becomes a serious issue for them in terms of their financial viability. So deploying this agent to learn the really good players' tendencies and then change the game to challenge them continues to be a key part of user engagement that our system allows for that hasn't been present in the past here. So that is really a great opportunity for us, and we're starting to pursue that. So that same user engagement model from video games, where you're learning the user and learning the tendencies and sort of personalizing the experience for them on a almost minute or by second basis, can be done in web marketing as well. Some of the great benefits of that are, you might click on something you like to buy and get a bunch of ads fed to you that way on similar products or the same product. But there's a frequency in which those ads become detrimental to your sales campaign. And we've modeled that and figured out how that communication method works best. The RL engine is able to work that out per person based on their tendencies, and feed them the correct amount of correspondence to make sure that they continue to be interested in your platform and the products you're selling in that platform. So that kind of personalization is sort of the next generation of web marketing. On the financial side, we are speaking to some companies about improving fraud detection. So the big problem with fraud detection right now is it sort of happens after the fraud is already finished. So millions of dollars are lost in that process of the detecting the fraud and doing some deployment, because it's just humans involved in every step of the way there. So our engine can learn all the frauds that existed over time, and learn what steady state behavior really is from when these financial transactions. And then when a new behavior is flagged and detected, it can then immediately put in the fix, to minimize the loss of any funds or breach of accounts. So that is a new feature for the fraud detection market based on RL and continuous learning. In the IoT space and the robot process automation space, so two big applications we're focusing on. There are more, but this is kind of what we're starting. First, in IoT space is building management, where you have a building with a couple dozen or even a few hundred systems that need to be looked at in order to manage the energy efficiency of that building and access to that building and maybe temperature control of that building. And so the way it works now is that's all routed to a control room, and there's some thresholds that are set, but there's no real learning there. So it doesn't learn the duty cycle of when people occupy the building or don't occupy the building. It just kind of runs on a time schedule. So our RL engine will learn when the building is occupied, when it's not occupied, beyond the schedule, but actually when it's occupied or not occupied. The influence of spaces in the building next to other spaces in the building that might be unoccupied or occupied, and how to tune the HVAC controls so you can get most out of the energy efficiency of that, but also other systems like battery management for backup systems and other things that are happening, where we can learn when to bring on greater power into the building during peak usage time. All of that is sort of done manually today with an operator or a scheduling program that doesn't really take any real-time data, it just does it based on time. So our engine obviously would do it based on learning the tendencies of how the users used that particular space. And then the network effect in one building learned can be applied to other buildings as well. In the robot process automation game, that's a software program with a script to fill in forms or fill in other data, so it can make it so the user doesn't have to do as much work to get an outcome. The problem with that, there's no decision in that process. So if the form's filled out incorrectly, or if the user data is unreliable, there's no judgment there. So an RL engine could actually look for those tendencies and help make that process much more smooth. That market is sort of rapidly growing right now. The three leading companies in that market are all going public this year. So it's a very interesting market as it grows into making decisions from just scripting languages. And the last one is the fitness market. Of course, there's lots of data being collected every day through smartwatches or smart rings on people that wish to stay in shape or just have good wellness for their life. But the problem with that data is, I have a couple of these devices I wear, is it just shows you in the data and says you make the judgment on what to do. There's really no coaching involved that is any type of personalization. There's some global coaching things, but that doesn't really help you as an individual. So our AI engine could look at that data. It can then make a profile choice on what's best for you as an individual for any particular moment of any particular day. So looking at your tendencies, looking at your sleep data, and looking at everything else in that process. I actually was involved in a startup before I joined CogitAI doing this exact thing. So the reason why I joined CogitAI is we really needed a reinforcement learning engine to make that work. Okay, so any questions now? That's the end of the use case discussion.
Good, and that's the end of our overview as well.
Okay, well, I've got a couple of questions, if you don't mind. I wanted to go back to earlier in the presentation. Really very interesting presentation. I appreciate it because it's very clear and helps you understand artificial intelligence in a more in-depth way, and it's becoming more important that people do that, even from outsiders' points of view. People, I don't think I've heard of reinforcement learnings before, but within that, there was something that you said about actionable intelligence or activity, or I can't remember what the phrase was, but what does that actually mean in terms of the robot? I think, or rather the system, the artificial intelligence system, gathers data and then it processes it, and then it becomes actionable. I don't know what actionable means. To actually,
Yeah, it's kind of a play on words in a way, because actionable is usually or often meant to be the data that that is well processed can lead to a good decision. But reinforcement agents, of course, make their own decisions and they take their own actions. So they're able to take their own actions. So we're using the word in a slightly different way. We mean that the AIs themselves are able to take actions and able to move the process forward by taking actions on behalf of an existing system. And in the process of doing so, of taking over that decision-making mechanism, they're able to improve the performance all on their own without involving humans in that loop. So they can take the actions, and like is shown here in this diagram on the right, they take the actions, the client's process executes those actions, and then and this process continues over and over, and they improve that process by way of this performance metric that's sent to them in the form of the reward signal. Dennis, do you want to say anything more about that?
Yeah, I think that's the key. That's the key aspect of this type of AI, both for reinforcement learning and for continuous learning, is the fact that the AI takes action and to make that decision. It's different than supervised learning, where the AI never takes action. It just does pattern matching and delivers that result to either a human or some kind of heuristics program that says, oh, we have a lot of cats we've detected, that must be a cat, right? So there's really no action there that's in a fine-grained decision-making sort of way. So this is like the key aspect of this second generation AI is the fact that it can make really, really good decisions and take really good actions.
So this brings me on to what I would probably consider to be a sort of mischievous or fun sort of question. Not so fun if you think about it from some people's points of view. The idea of computers and AI becoming autonomous and making decisions on their own, which are not consistent with the interest of, I don't know, people around them even, or the owners of the machine that's running the AI. And you know what I'm getting at? If it's,
I'm not hearing.
I'm wondering if it's still under control, and the parameters that you set for the actions are enough to prevent it from causing disruption, if not even harm.
So the answer to that question is when you set up the process for reinforcement learning, it learns both the reward, but it also learns that everything that's not a reward is something to be avoided. So it's going to learn the other side of that too. So it's going to learn how to not make bad decisions as a result of that. It learns the reward, and it learns that the things that are not the reward are things not to try again, right, in the process. So during the training scenarios, before you deploy an AI like this, you sort of vet out all of those scenarios in which you can have a cumulative negative answer producing a bad result in this process. And that doesn't take very long. It's maybe 100 hours of compute time or so, depending on the complexity of the policy that's being generated. So it learns in both directions. So that really is a positive thing. As long as it is the reward established correctly by the AI expert in your company, then there should be no problem with that negative results there.
Well, the idea is that you're actionable, and the idea of something being reinforcement learning based, and then being able to make decisions and take action more or less on its own. Obviously, that means it's not in the direct control. And people are concerned about computers having that much autonomy, certainly in some areas. But I was just wondering what, maybe I'm talking about a broader question rather than very defined areas where you're operating. But, you could sort of give me your comments about that.
Yeah, this makes sense. It's a good question. As soon as you pass over control of a process to an autonomous decision-making system that's learning on its own, then obviously you're doing something you've never done before, and you have to be careful about it. Now, the reinforcement learning system does have to experiment. There's no way that it can learn without doing a little experimentation. So it has to understand, well, what happens if I do this? What happens if I do that? Same thing as in the game of Go or any other game. It has to be able to figure out what are good moves and what are bad moves, and it does that by taking lots of different actions and seeing what results. So there are times when that is fine. It doesn't matter. It can make, there's no such thing as a really bad move, like learning to play a game. I mean, nothing's going to happen if it makes a really bad move, other than it'll learn not to take that move again. But there are other cases when you put something into an industrial or commercial application where it might make a mistake, and that mistake may not be something that it can recover from. In those cases, you have to be able to know in advance where it should and where it shouldn't be allowed to take its own action. So in most cases that we've talked to in commercial applications, if there's a sensitive process, then the clients themselves understand what the constraints are around that sensitive process. So they know that there are certain values that are not acceptable, certain values that will lead to danger, and they already have a controller in there already that's taking actions, and they already have constraints put on that controller, so that if it suggests an action that would fall outside of the safe boundaries, then that action is not used. And the same would be in our case. So we continually will suggest an action, makes a suggestion for the action, but then the client's own process gets to decide how to execute that. And that means including whether to execute that. So it might decide that this goes outside of the bounds of safety, and so it's going to use another action instead, which is fine. It's totally fine with us. As long as they let us know what actual action was taken, then we can still learn from that. And then the other way of dealing with this is that when we first start using the system in place, it shouldn't, if it's a sensitive, if it's being used in a sensitive process, then it already should be pretty good at that. So, and we can guarantee that by basically training it on the current system. So we give it as training input all of the current decisions that are being made, so that when it begins to take over, it's doing things more or less the way they've already been done. So it's not just starting from scratch and learning for itself how to do everything and taking all kinds of wild actions. Instead, it's taking really good actions. It's taking actions basically the same as already would be taken, but it's exploring a little bit around the edges, taking a little bit of actions within the constraints provided by the client.
If I could go back to your Go sort of allusion, I suppose we're talking about the famous sort of game between I think his name was Lee Sedol, the world's best
Yes.
Go player, human Go player, versus Google's DeepMind AlphaGo algorithm and the Google DeepMind AlphaGo algorithm 1, which many people didn't predict. And I was wondering whether a machine like that, this is probably outside of your sort of area, not your area, but outside of your product and development and research, but you know enough about artificial intelligence to be able to give us an interesting perspective on it. But I was just wondering, if a machine like this, and if an AI system, whether it's reinforcement learning or whatever you call it, learns the rules of a game and then plays someone like Lee Sedol, or whatever his name was, just learns the rules and then plays him, rather than go through the hundreds of millions of simulations on its own and trains and all that kind of stuff, how would it fare against a human? Maybe you could allow it to maybe simulate on the spot during the game a few different moves or a certain number of simulations before it actually makes its move. But say if it wasn't allowed to even do any simulation to begin with, just learn the rules, play the game. How do you think it would do?
Great question. In fact, I frequently pose that question to describe what the difference is between reinforcement learning and continual learning. So the bottom line is that reinforcement learning works fantastically well when you can play the game over and over and over and over again as many times as you want and learn about it that way. How you play the game, if you can only play it exactly once, that's a very close metaphor. I use that actually as a metaphor for the continual learning problem. And very few people are working on that, on trying to solve that problem. I'm not sure that a game like Go would be the best way to try to address that. I think there may be better environments, but the answer to your question is, if you use reinforcement learning techniques to play the game of Go exactly once, it will do a terrible job. It will not come anywhere close to beating anybody. It has to learn from experience. It has to play the game lots and lots of times, and it's through that experience of being in the same situation or very similar situations over and over again that it learns what to do in each situation. So that repetition is critical.
Yeah, I was being unfair. I mean, Lee Sedol, whoever the computer plays, would have practiced and played a lot. So yeah. It's unfair to say, well, the computer can't practice and simulate and whatever. It's just the volume of simulations, the games that the computer is capable of playing. It is probably hundreds of lifetimes worth of games that it can play within a few hours or a few days. So it therefore makes it so much more capable of beating humans. In theory, it seems. I don't even know the game at all, but you know, I don't understand it. I've tried to play it on computer. But the point is, you know, you can't see a human competing in those circumstances. If a machine can simulate possibly even billions of times, what chance have humans got, basically? Yeah,
so the other side of that coin is that real life isn't like that, right? Games are like that. Games are really repeatable, and you can play them over and over again. You can build a simulation that works perfectly. So we can build a simulation of Go, and it's 100% correct in every situation. But the real world never has that. We can't get anything to be the same twice. In fact, that's one of the reasons that that robotics is hard. I mean, even when we constrain a real-world system to be absolutely the same at every iteration as we can possibly make it, we find out that there are always little variations here and there. The real world changes. The world changes all the time. It's not just because the same situation is a little bit different each time, but because there really aren't very many of the same situations. Every day is different. You wake up in the morning, you read the newspaper, you get a totally different story, and that's why you read it too, because you know it's going to be different, and you're going to get new and different information from it. So the real game is the third generation. The real fun happens in the third generation when we start to deal with that kind of constraint. What happens if you don't get to play the game more than once? You just get to play it once, and you still have to do as well as you possibly can. That's kind of the game of life, and that's the game of trying to maximize the amount that you've learned so far to be used when you make the next decision. When we get into real-world commercial applications, we're going to find out that in many, many cases, every situation is going to be new and a little bit different, and we're going to have to use this sort of continual learning approach. We're going to have to try to make use of everything that's been learned so far to deal with a new and different situation. Some of those cases are going to be like the reinforcement learning case, where we can repeat the same process again and again. But many, many cases are not going to be like that. And so your question is exactly right. What do we do then? And that's part of our ambition, is to deal with those situations.
Okay, thank you for that insight, and I apologize for sort of asking these very broad questions, which I'm sure you thought about yourself. Everybody does, but whether it's directly commercially relevant to you and your business, I don't know. But just getting back to that, actually, I was curious about how much Sony invested in, what your turnover is, or any numbers that you can provide in terms of business, and what your customers are. And I mean, it sounds to me like you're still sort of researching, in research mode and testing mode. But I'm sure I'm wrong. You probably have very lucrative commercial agreements with businesses. I don't know if you want to shed light on any of those things.
I'm going to turn this question to Dennis. I think he can get it across most succinctly.
Yes. So we haven't disclosed the amount Sony has invested into us publicly, so we're not going to do that without Sony's agreement there. So that's one answer to that part of your question. The second is, we are involved, as I mentioned, in part of the use case discussion with contracts already during the time that we were building the platform here, with customers that wanted to engage with us early in this process. Those customers have not announced their products, and therefore we can't talk about their programs in detail, but we have traction in the market already for CogitAI's products and offerings.
Right. I think last question that I can think of. I was curious. AI, generally speaking, I imagine depends on being able to collect vast amounts of data, not just in terms of raw data about operations, but also the other computing systems, operating systems that you might have to work with. And from what I know, in the industrial space, there's a lot of proprietary operating systems. Each robot has company has its own operating system and IoT platform and things like that. I was just wondering how easy would be or is already to work in an environment like that, or am I wrong? Is it fairly open now? Is it possible to find ways to connect to a variety of different platforms?
Yeah, so it's a cloud service, and that means that we just have an API. It's accessible from any operating system at any point. Any operating system can interact through the cloud service API, through the RESTful API, and accomplish the same things as any other operating system. Now, we do have a client package that has to be that is best downloaded onto the client's computer, so that the client can interact most efficiently and effectively with Continua. That's all written in very easily transportable code, so it runs on pretty much any system. It's all Python, and the Python systems that it installs with are all readily accessible. So it makes it pretty easy for any client to be able to interact with our cloud service.
You see, it is an interesting area. I know a lot of stories have been emerging about the idea of using AI to make industrial processes more efficient. Do you find yourself competing with people like ABB and, their platform, what's it called, ABB Ability, and then you got GE Predicts and things like that? They probably have AI elements to them, don't they? The idea of connecting up all your machines into Predicts and then having an AI system decide how to manage it, which machines to switch off and which machines to keep running, and so on. That's probably something that an AI system could do. But I don't know if that sounds familiar to you.
Yes, it sounds familiar right now. That is a kind of a supervised learning application through GE. So you basically, every machine you connect to it is tagged. When that machine is not in use, it can tell, and then you can make some kind of power management scheme for that. So GE would be a customer of this platform, right? To add some further intelligence into that process where our reinforcement learning engine would learn how their software would work and then manage it much smarter than what's going on right now, which is sort of the kind of that scripting language I talked about earlier, kind of robot process automation. That's a form of what GE is doing. So we are sort of the next generation of all of that thinking. So that thinking about using an AI to do some sort of pattern matching, but after the pattern matching is done, you have to make a decision, and to figure out which decision is best is what our AI is really good at.
The bottom line is it's a horizontal platform. It has a broad number of possible use cases, and those use cases can have a number of different characteristics, from being very low bandwidth with low latency requirements, that is to say lots of latency flexibility on the one hand, to, on the other extreme, very high bandwidth. Decisions have to be made very quickly with very little flexibility. For example, robotics on that end. And our platform is set up to cover all of these different cases, so it can do computation at the edge, it can do computation in the cloud, it can do make the decisions at the edge of the cloud, it can create models or policies that are downloaded into an edge device, or it can do all of the policy calculations in the cloud. So it's very flexible. It can be applied to a large number of different use cases. And what's cool about it is that those use cases cut across sectors, across markets. They can be throughout industry. We think that the opportunity here to bring a new kind of AI into a part of industry that's not really being touched by it yet is enormous.
Overall, I think that the technology that we're bringing, and if I leave you with one thought, is moving from the sort of face detection, pattern matching level of AI that you see today in everybody's everyday products and everyday services, to the decision making and smarter process optimization part of AI, which is what this technology is really engineered to do.
Okay, thank you very much, both of you, for your time.
Send us an email at sales@roboticsandautomationnews.com to register for one of our many upcoming webinars. And if you'd like us to host your webinar, we have a range of options, including long-term lead generation packages and marketing campaigns. We look forward to hearing from you soon.